Pythagoreans thought was that since number kind of ruled everything, then everything could be represented as an integer. Okay, so here's one way that this played out. One line of thought that they had was they started some geometrical problem, and if they had they had some implicit unit that they were going to measure things with, and the underlying assumption was that everything in this problem could be measured with that one unit. Okay, and so this is actually a problem, and this is related, or it's equivalent. The fact that you can't do this is equivalent to the fact that the square root of 2 is irrational. And I'm going to show you sort of a geometric proof, but you can see how this translates really easy to the common proof that we know today, that the square root of 2 is irrational. There's a lot of overlap here. So I'm going to begin with a square. Like this. I'm going to do my best to draw a good square. And I'm going to have it on its side like this. Now, the statement of the theorem, the square root of 2 is irrational. We're not going to prove that statement. What we're going to prove is the following. Let's say I label this A, B. Let me put, actually, it's probably going to be easier if I put them on the inside here. A, B, C, D. The way that I want to state this is there is no common measure to measure the side length AB and the diagonal AC. So there's no common measure to measure A, B, and CD. In other words, there's no piece of string that I can cut such that there is an integer number of that pieces of string going from A to B, and there's an integer number of that pieces of string going from A to C. Okay, so in other words, these are not co-measurable. They are not commensurate. This side length here and this diagonal here. Okay, this is what it means. This is one of the things that this is one of the implications, or one of the ways to say that the square root of 2 is irrational. If the square root of 2 was rational, then we could find, if you had a square of side length 1, we could find a common measure such that each side is an integer number of that units. Okay. And I will leave it to the discussion to sort of work out the details about how those are connected, or about why those two statements are equivalent. Okay, so here's how we're going to prove this. I'm going to start by very carefully drawing a dashed line here, drawing a dashed line here. Of course, this length and this length are the same, and what I want to do is kind of fold this triangle out this way. And so we're going to get a triangle like that. I'm going to fold this out like this. I'm going to go over here. Like this. Okay, now this outer square, let's see, A, B, C, D, E, F, G, H. Now this outer square, by the way that we constructed it, is double the area of the inner square. Okay, so the area of the outer square is double the area of the inner square because we're just, unfolding each one of these things. We do that for each part of the square, and so the area of the outer square is double the area of the inner square. So I'm going to write that down right now. So this distance right here is also the side length of the outer square. So what it tells us, I'm going to use maybe a marker that shows up a little bit better. So what it tells us is that dB squared is equal to 2 times AB squared. Okay, so we're just recording that information. Now here's what we can assume. We can assume that either AB or DB, so this is the side length and this is the diagonal, we can assume one of those is an odd number. So I guess really what we're doing, I forgot to mention this, there is no common measure. We want to, let's argue by contradiction and assume there is. assume there is a common measure. Now what we can do is we can assume that either AB or DB is odd. Now why can we assume that? And again, think about how this relates to the square root of 2 is the irrational proof. We can assume that AB and DB are odd. If it isn't odd, if they're both even, if one of them is not odd, that is if they're both even, then we can just double the size of the measure and use a bigger measure. Okay, so we're assuming there is a measure, and we're kind of using the largest common measure that we can. Again, if A and B and D and B are both even, we can just double that measure and use that measure instead. Okay, so we're going to assume that they're both odd. Or sorry, assume at least one is odd. Assume that DB or AB is odd. So we're going to assume that DB or AB is odd. Now let's look over here. This says DB squared is equal to 2 times a square. So DB squared is equal to 2 times a square. So what does this mean? It means DB squared is even. So what does that tell us about DB? Well, remember we saw in the previous video that if DB is odd, an odd number squared is an odd collection of an odd number of items, so it's also going to be odd. So it means DB is even. So it means that DB is even. So we're assuming that either DB or AB is odd. So what is this going to tell us about AB? Well, DB is even. If DB is even, then DB squared is a multiple of 4. If DB is even, then DB squared is a multiple of 4. Okay, well, what does that mean? If DB squared is a multiple of 4, okay, we think about there's 4 different collections of the same size. Let's say K objects, K objects, K objects, K objects. 4 times K is equal to DB squared. DB squared is a multiple of 4. How does that relate to AB squared? Well, notice what this tells us is AB squared is equal to DB squared divided by 2. So just half of these collections. Let's say those 2 collections. Well, that's an even number. Because there's, we could just do the pairing thing here. So this is an even number. So this is even. So AB squared is an even number that's also squared. It's an even squared. So what this tells us, again, anytime we have an even number that's a square, it means that the number, AB in this case, is also even. That violates our contradiction, that they are both odd. Okay, so here is a proof here that the side length and the diagonal of a square are not commensurate. That is, there is not one measure such that this side length is an integer number of that measurement and the diagonal is an integer number of the same measurement. Now this is not quite the statement that the square root of 2 is irrational, but it's equivalent. Though maybe there's a little bit of argument that needs to be done to get that equivalency.